Hi Bobcats! In this video we're going to take a look at what VSEPR predicts for having 4, 5, and 6 domains. With 4, 5, and 6 domains, we're actually no longer going to have planar structures. We're going to have structures that punch out into 3 dimensions. And so to help us with these 3-dimensional structures, we're going to also look at some standard notation that is used for drawing these structures in 2 dimensions, like on a test paper. To start with 4 domains, you might think that following our previous pattern of linear and trigonal planar, when we bring that 4th domain into the mix, the 4 bonds just point towards the corners of a square, something like what we're showing here with this Lewis dot structure. If that were the case, the bond angles in methane, or CH4, would all be 90 degrees. And it turns out that we can actually increase that bond angle, so increase the separation between the domains, if we push and pull these bonds into the 3rd dimension. So right now they're all 5 of these atoms are all in the same plane. So what I'd like for you to think about doing is taking that top hydrogen atom and pulling it towards you. And ditto with the bottom hydrogen atom. Think about pulling that towards you. And then these 2 side hydrogen atoms, let's push them away. Let's tuck them back behind the computer screen. When we do that, we end up with a structure that looks something like this. In this sort of notation, the solid wedges, like we're showing up here on the top and down on the bottom, mean that the atom is coming towards you. So the outside atom, the hydrogen, is coming towards you. The dotted lines, like we have down here, mean that the outside atom is going away from you, so it's tucked back behind the computer screen. Now, normally this type of structure is written a little differently. It's written like this. When we draw it this way, the top hydrogen, the carbon, and the hydrogen to the right are all in the same plane. And we can see that's actually a bit bigger than 90 degrees. Turns out it's 109.5 degrees. And it doesn't matter which set of hydrogen, carbon, hydrogen bond angles we look at, they're all the same. They're all 109.5 degrees. This shape is called tetrahedral. And so with 4 domains, our geometry is going to be tetrahedral with a bond angle of 109.5. And this is the first one of our VSEPR shapes so far that actually requires 3 dimensions. So to help you remember how to interpret these VSEPR drawings, first of all, a plain old line is in the plane of the paper. So over here on the side, I'm going to draw, we had a carbon in this methane molecule. We had a hydrogen that was going straight up, so those 2 would be in the plane of the paper. We had one down and to the right. So all 3 of those atoms are in the plane of the paper or the plane of the computer screen. Then a solid wedge extends in front of your paper, closer to you, or in front of your computer screen. And so we would draw that in methane for the bottom left one that's closer to you. So there's our solid wedge. And then if we draw one with a dotted wedge, or when you draw this by hand, you usually just draw it with a dotted line, that means that that one is tucked back behind the computer screen. And a tetrahedron is just kind of a weird shape. That's not something you commonly encounter. It's not something like an octahedron, which an octagon, which you see on a stop sign, or a cube. A tetrahedron is kind of an unusual shape. In the case of 5 domains on that central atom, we need a 3-dimensional structure for its VSEPR structure, and we're also going to have a couple of different types of positions in our VSEPR structure. So let me start by drawing the phosphorus atom that's at the middle of this PCl5. And we're going to have 2 atoms that make a line with it, one going straight up, and there's our Cl, and one going straight down. There's our other Cl. So those 3 are all in a line, and they're all drawn as being in the plane of the paper. I'm going to stick one more in the plane of the paper, and I'm going to show that going out to the right. So far what I've drawn is showing us that we actually have a bond angle of 90 degrees. I'll come back in and label those bonds in just a moment. But let me draw in the remaining two chlorines. Those remaining two chlorines are going to pop out into 3 dimensions. So one of those chlorines will be over here to the left, coming out towards you from the computer screen, and the other chlorine will be going back behind the computer screen. Now, this essentially gives us two types of positions. The ones that are going up top and down below are referred to as axial positions, and the remaining 3 are referred to as equatorial positions. For the bond angle between the axial and the equatorial positions, we're looking at 90 degrees. But for the bond angle between one equatorial position and another equatorial position, we're actually looking at 120 degrees. So those 3 equatorial positions form an equilateral triangle. And they're within those positions, you actually have a trigonal planar shape. And then the axial positions come in perpendicular to that. So we have a mixture of bond angles here. If you go from axial to equatorial, it's 90 degrees. If you go from equatorial to equatorial, it's 120 degrees. And then if you go from axial to the other axial position, that's actually going to be 180 degrees. So that 180 degrees is axial to axial. Now the name of this strange shape is called trigonal because of that axial, that equatorial plane, and then bipyramidal. Hopefully I can help you visualize that a little bit. It's trigonal because we have this triangular shape in the middle, and then it's a pyramid because if you look at the 3 equatorial chlorines plus the one on top, that one on top forms the tip of a pyramid, but the one on the bottom forms the tip of a pyramid as well. So that's where the bipyramidal comes from. We have a pyramid pointed towards the top, and we have a pyramid pointed towards the bottom. This is sort of the idealized geometry for trigonal bipyramidal. It's kind of interesting to note that there's some experimental evidence that indicates that this may not be a very accurate description of having 5 domains, but that's a topic for an advanced inorganic chemistry class. So if you're intrigued by that possibility, come be a chem major and you'll learn about this in the upper level inorganic course. For the expanded valence compound that has 6 domains, something here like SF6, we go back to having a fairly symmetric VSEPR structure. We're going to have the same bond angles all over the place in this one, unlike the trigonal bipyramidal where we have different bond angles depending on the different positions. I'm going to draw the sulfur that goes right in the middle. And like we started with on the last slide, I'm going to draw one going straight up, and I'm going to draw one going straight down. Now there are a couple different ways that this shape gets drawn. I'm going to go with the one that I like the best, which is to think about the remaining equatorial type positions as forming a square as opposed to a triangle, back with the trigonal bipyramidal structure. And we're looking at it sort of edge on. So I'm going to draw that square as sort of a big X going through that sulfur. And so then we'll draw the fluorines here. Now in the plane of this, these equatorial positions, the bond angle that we're talking about will be 90 degrees. because it's a square planar sort of thing. And if we're looking at one of these axial positions going down to one of these equatorial positions, that's going to be 90 degrees as well. So really, we don't have equatorial and axial positions. All of these positions are exactly the same. They're all equivalent. Sometimes when people are drawing an octahedron, I'm sorry, I didn't mention that yet. The name for this shape is octahedral, or the adjective form is octahedral, the noun form is octahedron. Sometimes as a shortcut in drawing these, people will draw an X that's kind of squished a bit, and then we'll draw a line through the X to show these shapes when you're drawing them by hand. And so we'd have sulfur at the middle, and then our 6 fluorines surrounding it. All right, so that is what we do with 6 domains. In this video, we showed that if you have 4 domains, we're going to have a tetrahedral structure. The basic shape for a tetrahedron would be something like have some atom A in the middle. We draw a regular line straight up, regular line down to the right, then a wedge down to the left, and a dotted line down to the left. In the case of 5 domains, we called that trigonal bipyramidal. And with the trigonal bipyramidal, we have 2 different types of positions. We're going to have the axial positions that go up and down, and then the equatorial positions, which are basically forming an equilateral triangle perpendicular to the axial positions. And then with 6 domains, we called that shape octahedral. And we would draw it with kind of a squished X with a vertical line. Whoops, I kind of missed. Let's try that again, see if I can draw that a little better. And have a X here with a vertical line going through it. Still kind of missed. And with the central atom being at the intersection of those lines, and then the 6 surrounding things at the ends of those line segments.